Hi everyone, am I audible? Okay, cool. So we can get started. Yeah. So happy New Year, everyone. And in this new year, let us begin with something new. So I think we were done with dynamic programming. I had also asked you to go back and take a look at this well-known question called as edit distance. How many of you were able to take a look at that? You can type yes if you were able to. Okay, good. I want more people to take a look at it. Only if almost all of you have taken a look, we would be discussing it in the class. And others, if you have any difficulty, feel free to ask the questions. So for now, let us get started. Today, I want to talk about very simple but very useful data structure called as stacks and queues. So among these, I'll start with stacks. So tell me, what is a stack? Define it yourself. Okay, most of you are saying LIFO. Okay, so most of you are saying stack means LIFO. Others who don't know, LIFO is last in, first out. Okay, so it says that stack is a data structure in which the element which is last in, that is the element which will first be out. So for instance, if imagine this is a stack of numbers, so you are just inserting the numbers inside it, like you insert 5, then 1, then 2, then 4. So what is the last number that got in? Last number that got in is 4. So while you will be removing the elements, 4 will be the first element which will get out. So whatever was last in, that is the first out. You can tell it in a different manner also. You can also say it first in, last out. It means the same thing. The first element to get in was 5. And while you are emptying it, 5 will be the last element which will get out. So the key thing to keep in mind over here is stack is super useful whenever you want to ensure that the order of deletion or order of taking out is opposite of order of insertion or order of getting in. So your order of insertion was like 5, 1, 2, 4, but your order of deletion will be 4, 2, 1, 5. Does that make sense to everyone? Yes or no? Yeah. Okay, cool. So one more thing that I wish to talk about is in stack, there is only one end, which is mobile. I mean, there is only one end that changes. So this is the same end where deletion also happens. When you delete something, the stack shrinks. And when you insert something, the stack grows. So there is only one end that keeps on changing. So this is one-ended data structure. Now, can you give me some real life examples of stack or some programming constructs where stacks are used? We're saying routing, what kind of routing? Recursion, yeah. Recursion is a very well-known example of stacks, and I think we have discussed a lot about recursion, so you should be able to relate. When functions call one another, so like Fibonacci, you remember, f of n calls f of n minus 1, and then f of n minus 1 again calls something, again calls something. Those functions are lined up in a stack. And when the functions return, then the last function to get called will first return, and then the previous one, and then the previous one. That's how it happens. So recursion is one example. Apart from that, there is one more example that you might be using on a day-to-day basis. Yeah, one of you is saying browser history. Yeah, quite similar, but something simpler than that. Editor. Okay, so in editor you might be using, how many of you are aware of this thing called as undo redo? You must be using that, undo operations and redo operations. So let me give you an example. Let's say there is a text file, and this text file is initially empty. Now, whatever actions you perform on it, your computer records them in form of a stack. So for example, there is a stack and computer kind of remembers that, hey, initially the file was empty. And then you write A. So computer remembers, okay, somebody wrote A. Then you write B. So computer remembers somebody wrote B. And then you write C. So computer remembers somebody wrote C. So now tell me, this is your file, you have written ABC. If at this point of time you do undo, what will happen? ABC will convert to AB, right? C will be removed. So when you do undo over here, this thing will go away. And how this thing goes away is, this thing is popped from the stack and maybe pushed in another stack for meanwhile. Why it is pushed in another stack, I'll talk about that later. But tell me, if you do undo again at this point of time, one more undo, what will happen? This B will also be removed. Okay, removing this B means this thing gets popped off and all that is visible is this much. Okay, at this point of time, if you do a redo, what will happen? If you do a redo, the B that got removed will come back again, which means this thing from here will get pushed in this stack. If you do a redo again, then this thing will get pushed onto that stack. Is that making sense? How many of you are able to understand regarding these undo redo operations? Yeah. So similarly, there are many use cases where stacks could be useful. The key thing to understand is that if you technically look at undo operations, it's like think of it like event 1, event 2, event 3, event 4. Now, when you are undoing event 4, you want to get to event 3. So you just want to get to something that lies below you. Okay. So reading a question, figuring out such use cases, you will be able to figure out whether the stacks are to be used here or not. So now let's come to the programmatic definition of stack. Okay, so there are many ways in which somebody can implement a stack. One of the ways in which you can do it is, can you confirm undo redo example stack? I did not get your question. Why you think it is to be implemented using linked list? You give me the reason behind using linked list. Yeah, if you do that, I'll come back to it. Okay, cool. So now, as I was saying, if you have to implement a stack, there are many ways to do that. What according to you should be the easiest way to implement it? Using an array. How many of you have implemented stack at least once? Yeah. Okay, good. So I can say, let's say there is an array. So array generally is drawn like that. So now because we are learning stacks, so let me turn it a bit. So it has got different indices. Let's say index 0, 1, 2, 3, 4, and so on and on and on. Now in this array itself, what you can do is you can push your element and you can pop your element. So push will mean you are trying to insert, and pop will mean you are trying to delete. Okay. So whenever you push something, let's say you push 7, it comes here, you push 9, it comes here, you push 1, you push 5, you push, and you keep pushing on and on, right? So this is how things grow. Now, so array is essential. I need an array of some size. For now, let's take big enough size, let's say 10 power 5. It can be higher depending upon how many elements you are planning to insert. But apart from this, I need one more thing. And what is that one more thing? I also need to keep track of top. Top is a variable which will point to the index till where the array is filled, right? So you need to have a top as well. Because think if you do not know what this top is, what will be the next place where you will insert the element? You will not be able to figure this out, because if at some point of time, let's say I decide to kick this element out, I decide to pop this, then it's your responsibility to change your top. Because if you do not change your top, how will you make sure that next insertion will happen at 3? So you have to keep track of this top. And it looks like whenever you will insert an element, you will increase your top. And whenever you will delete an element or pop an element, you will decrease your top. So I need to have this variable. Now these two things can come inside a struct. So let's call it struct stack, right? The way you had created struct for a node or class for a node, you can create the same thing for a stack. Is it making sense that why do we need these two things together for implementing a stack? Yeah. Okay. Now, in context of an array, the index starts from 0. And if stack is empty, that means if the stack is empty, it means we need to initialize top to some value. So what is the right value according to you, which it should be initialized with? Yeah, so you can initialize it to -1. Why -1? Because, so let's say you declare struct stack s, right? Now, after you have written this piece of code, it means that in your computer, memory has been allocated for an array of the defined size, and memory also has been allocated for an integer variable called as top, right? Now you can do s dot top equals to -1. Why -1? Because we all agreed that whenever we'll push something, we will do top plus plus. So if you insert your first element, then doing s dot top plus plus will make sure that your top will immediately start pointing to this. Okay, that is the reason -1 is probably the best choice over here. Cool. So now it all looks good. If I ask you that, hey, honor that signature of the stack and implement the different functions for the stack, will you be able to do that? So let's quickly take a look at operations. First operation, of course, is push, and then pop, and then you have got something called as, it is called as peek also, and it is called as top also. And then you have got an operation called as is empty and is full. See, the name of these operations can vary from language to language. It depends upon what language you're using and what name was given in the library of that language, but the essence remains the same. So can you implement these things on your own? Yes or no? Yeah, can do it. Okay, so let's start implementing this push. So I would say, let's say there is a push method. Push method does not return anything. Push can be thought of as a write operation. WRIT, right? It is changing your stack. It is not reading something from it. So while you are pushing, let's say, an integer x into this stack which you have defined, tell me what should be my first line of code. Yes, the first thing is to always check whether my stack is full or not, because who knows that this array that you are using to implement the stack is currently at its full capacity. So in that case, if you try to push something, you won't be able to do that. So that is an overflow state, right? So you might have heard of things like recursion overflow and things like that. So recursion overflow happens when you miss out on a termination condition. If you write a recursive code in which there is no termination condition, you will see that a function calls another, that calls another, that calls another, and that stack keeps on growing, right? And it becomes of infinite size, and then your program kind of crashes. Okay, so first you need to have a check for overflow, and let's say there is an is full function. I'll implement it later, but you can make a call to that. If is full, then you can print that, hey, we can't push, it's an error scenario or something like that. Only if it is not full, in the else case, you can go and you can do certain things. So see, this array is present in this within this structure. So I have to use dot operator to access this. If you know how to use objects or stacks things. So you can do s dot array. And now you also need to increase your top. So I can do plus plus s dot top equals to x. That's it. This one liner will get your job done. So in this one line itself, what you have done is first you have done plus plus s dot top. So your s dot top has increased. And then at that slot in the array, you have inserted the desired element. So this can be our code for pushing an element. Is it making sense to all? Yes or no? Yeah. Okay. Cool. What to do in case of pop? So let's say you want to pop. Pop again is a read operation. Should it take some argument? The answer is no. So what will be the first line of code in the pop? Yeah, to check for underflow, because if the stack is already empty, then there is nothing that you can remove from it. And let me tell you one thing. This is the most practical mistake that people make while writing their programs. So people write their programs where they might not be creating an infinite stack, but certain times they have to remove elements from the stack. Whenever you make a note of this thing, the errors that you will make in future, I guarantee some of those errors will be this, that you are popping from an empty stack. You will certainly make this error, even though we are discussing it right now. So yeah, so the first thing that you will check over here is underflow situation. So you will say if is empty, then you will print some error, not do anything. Otherwise, what to do? In the normal case, what will you do? Yeah, s dot top minus minus, because if let's say you want to remove element from here, all that you have to do is you have to come down by 1 unit. Coming down by 1 unit means s dot top minus minus. One of you is asking me why to initialize s dot top to -1. Okay, you try initializing it to something else and then see what happens. You want to initialize it to something like 5. If you initialize s dot top to 5, it means that your stack is full till 5. Is that the case? The answer is no, because initially your stack is empty. Can you initialize it to 0? If you initialize it to 0, it means at 0 index you already have an element. So what do you want to initialize it with? Think of that. Okay. Cool. So these two operations are clear to everyone, push and pop. Then you have got something called as peak or top. So what this does is, this does not remove or add anything to your stack. It just tells you what is the topmost element. Because remember, in a stack, you just have access to the topmost element. So what to do in this case? Do I have to make some check, or do I have to? Yeah, I have to check for underflow again. Yeah, because if the stack is already empty, there is nothing at the top. So if is empty, then you print your error or whatever. Else, what to do? Return s dot array s dot top. So whatever is at the top in the array of the stack, you turn that. Okay. Can you implement is empty is full? Again, very easy. So bool is empty. So if you're talking about an array implementation, you can say return top greater than equals to 0. Sorry, return top equals to -1. So if at any point of time your stack dot top is equals to -1, that means the stack is empty, right? And similarly, you can implement is full also. So let's say if it is full, let's say if the size of this was n, you can say if s dot top at any point is equals to n-1, because that is the last index, then you would say it is full. So these are all the important operations of the stack. So these are, the actual operations of the stack. Somebody might in future ask you that, hey, I want a new operation. So any new operation that you will do on the stack, that new operation will be born from these only. You have to combine them and create a new operation. Okay. Are these all clear to everyone? Yes or no? Okay, can you quickly tell me what is the time complexity of each of these operations? Order one. Everywhere it is order one because you are just dealing with the top part. You're just adding at the top or you're just removing at the top. You're checking the size. It's not going to take you more than constant time, which is order one. Okay, so stack is a very powerful data structure because of its low cost of operations. Okay, now I had told you one thing. It's a very well-known interview problem where interviewer will ask you that, hey, there is a stack and I want to introduce a new operation apart from these operations in the stack. Now, in that, people try to do random things. So you don't have to do random things. You have to make use of these operations and then you have to implement that. So I'll come to that. But before it, whenever you are solving a question that you believe can be solved using a stack, you don't have to create your own stack like that because it will consume a lot of time. So there are stacks which are already defined in your libraries. You can use that. For example, if you are a C++ user, you can do stack of integers if you are dealing with integers and name it S. Now the well-known operations on this, as I told you, first is s.pop. Make sure before doing it, you are checking whether your stack is empty or not. Okay, you have s.pop and then you have s.push. You can push an element X, and then you also have s.empty. Using s.empty, you can check whether stack is empty or not. So it returns true or false. And then finally, you have s.top. S.top simply returns you what is the topmost element of the stack without disturbing the stack at all. So these are the 4 key operations that we'll be using with this inbuilt stack of ours. Now, how this inbuilt stack is internally implemented by your language, we are not going to get into that. It depends upon the language. If you are curious, you should definitely read about it. Okay, using array is one way. Using linked list can be another way. There are several ways. Okay, cool. So now let's come to a question. Keep it in your mind. You're using this stack. It means at any point of time, you can only access the topmost element. You cannot, so if let's say the stack contains 1, 2, 3, 4, 5, and you can't just insert an element between 2 and 3, or you can't insert an element after 4. You can't do that as long as the topmost element of the stack is 5. So let's come to the first question. We want to implement a new operation called as push bottom. So push bottom should take an element X and it should push this X to the bottom of the stack. For example, if I want to do push bottom of 6 to this stack, then what should happen is that everything else remains the same. It's just that 6 comes to the bottom. Do you understand the meaning of push bottom? How many of you do? Just type in yes or no. How many of you can implement push bottom? Tell me, what is the idea that we can use here? Okay, take another stack, use 2 stacks. Okay, cool. This is the easiest question on the stack that we have started with. And let's quickly talk about that. So guys, tell me one thing. As long as this stack is not empty, answer my question. As long as this stack is not empty, can you push 6 to the bottom? Yes or no? The answer is no. The first thing is that empty this stack. Okay. Now keep one thing in your mind. If you empty this stack, you might lose sight of all these elements, which you don't want to lose sight of. Because after emptying it and pushing 6, you want to ensure that these elements get pushed again in the same order. So what I'm going to do is, as all of you are saying, I'll create an auxiliary stack. And while I'll be emptying this stack, I'll be pushing the elements into this. So see, what will happen is when I remove 5, this 5 comes here. When I remove 4, it comes here. You remove 3, it comes here. Similarly, you remove 2 and 1, they come here. Okay, did you observe one thing? That currently this stack looks like reverse of that. You should be able to do that, right? Because whatever was there at the top, that came at the bottom, and whatever was there at the bottom, that came at the top. Okay, now that this stack is empty, so I'll now push whatever I actually wanted to push, which is 6. And after pushing this 6, I can again empty this stack and push its contents into that. So now I'll put this 1, then 2, similarly 3, 4, and 5. So this is the key idea. So we have been able to push an element at the bottom of a stack by using another auxiliary stack. The first step is that you create auxiliary stack and empty your current stack. The second step is that you push your X once your current is empty. And the final step is that you empty your auxiliary stack and push the contents into current stack. That's it. Okay, does it make sense? Yes or no? How many of you get it? Yeah, simple enough. Okay, cool. The important thing that I want you to keep in mind is that because while emptying the current stack, I had pushed its element into the second stack, so the order 1, 2, 3, 4, 5 did not get violated, right? Because you remember when you had emptied it, what had happened was that this 1 had come to the top. And why will it not come to the top? Because it was the bottommost element. Now, when you push it again, it will again go to the bottom, right? And 5, which was initially the top, had come to the bottom. And when you empty it, this 5 will automatically come to the top. So in a lot of questions, you will realize that you might have to use 1 extra stack or 2 extra stacks or 3 extra stacks. And using them, you'll be able to solve certain problems. Okay. Okay. So can I solve this question using recursion? Okay, so one of you is asking this question that can we shift one element and add 6 at 0? Tell me one thing, if you're using this stack, inbuilt stack, do you know whether it is implemented using an array or linked list or whatsoever? Do you know that? Yes or no? You don't know that. Do you even have access to how it is internally implemented? Do you have access to the array that the library is using to implement this stack, to the linked list that the library is using to implement this stack? No. So how can you manipulate this internal array or internal linked list? You can't do that, and it is not allowed. In a stack, you should not be able to alter the elements like that. You have to implement a new operation by using standard stack operations only. And those standard stack operations are the ones that we learned just now. Is it very clear to everyone? Yes, no? Yeah. So never make this mistake in your interviews where you tell your interviewer that I'll manipulate the internal array or something, because that will kind of showcase that you don't really know that what is the purpose of using stacks. Okay, cool. So yeah, I was asking, can I solve this question using recursion? How many of you can do that? So what recursion does is it internally creates a stack. So right now you are solving this question by creating your own auxiliary stack. But what if recursion creates that auxiliary stack for you? It will be great, right? So what we will do is, let's say you want to push bottom something. Let's say 4 in a stack that contains 1, 2, 3. Okay. Think of it like a function call. Okay, so there is a function which takes 2 things. The first thing is an integer which you want to push bottom, and second thing is your current stack in which you want to push bottom. So what I'll do is I'll say that, hey, I cannot push this thing to the bottom until unless this stack is empty. So in every step, I'll try to empty it by 1 unit. Empty it by 1 unit means whatever is the top element, let's just remove that. So just remove it and this 3 comes out. Now store this 3. Do not let go of this 3 because you want to push it later. Okay. So I'll remove this 3 and then what I'll do is I'll call this function again on the remaining stack. So the remaining stack will now be 1, 2. Why? Because 3 has been removed. And now think of it in this manner. See, how recursion works is it delegates a bigger problem to a smaller subproblem. So it's like, let's say this thing somehow happens correctly. You want to perform a push bottom of 4 in this stack. Let's say this magically somehow gets happened, then what would actually be the state of the stack would be something like this, that this 4 would have gone bottom and 1, 2 would have remained as it is. Now, if this somehow magically happened, then after that, you just need to do one more thing. Can you tell me what should that one more thing be? Yes, that one more thing should be to push whatever you had popped. So I had told you, whenever you're popping something, please store that with you because you want to push it at a later point of time. Now, what is that later point of time? That later point of time is that when this problem has been solved. So imagine this has been solved to this. So now you can just perform a push of 3, which is push of whatever you had popped and your job will be done, right? So just see how it will happen. So this function pops 3, remembers 3, and then calls push bottom on this. So that push is waiting for this function to end. Now this function again will do the same thing that this function did, which is it will pop. After popping, it will get 2, and now it will call push bottom again on the remaining stack. And after that, it will push 2. And now here again, what will happen is you will pop, you will get 1. And now you will call push bottom on the remaining stack, which is empty. And then you will push whatever you had popped. So see, this function called that, this called that, and this called that. Okay, what should I do here? Should I try popping something from here again? The answer is no, because at this point of time, my stack is empty. If your stack is empty, what are you waiting for? You can just push whatever you wanted to push, which is X. So at this termination condition, I can just push the element that I always wanted to push. Now this gets over. So now this push happens. So 1 comes on top. And then when this gets over, this push happens. So 2 comes on top. And then this push happens. 3 comes on top. The job gets done. Is it clear? How many of you understood how recursion also can ensure this thing? Yeah. So what happens really in recursion is that the stack of calls is created where push of 1 happens first, then push of 2 happens, and then push of 3 happens. Okay. And push of 4 is something that first happens on the empty stack. So those of you who have learned recursion sincerely, solved your questions honestly, you'll be able to really appreciate how recursion can be pretty useful in solving these questions. So whatever you can solve using an additional stack, you can solve it using a plain recursion also. Okay, cool. Let's move on to the next question. But before that, let's try to write the code of it. Okay, so let's say you want to write a push bottom method. It does not return anything. Okay, the arguments that you pass are integer x, and there is a stack that you are passing by reference. Okay, tell me what will be your first line of code? Base case. And in this situation, what is your base case? The base case is to check whether your stack is empty or not. Okay, so let me check. If at any point of time my stack is empty, what do you think should I do? You push what you always wanted to push. So you will do stack dot push of x, and after that you will return exit. Okay, otherwise what to do? So otherwise in situations like this, what is the first step that you take? The first step is to get access to the topmost element. Yes, see, do not pop directly. Here I have written this just for your convenience. Do not pop directly, because if you pop directly, you will forget what was the top element. So first read what is the topmost element, and that you can do using top. So if you do stack.top and store it in maybe y, and after this you can do stack.pop. So see, what has happened is, when you combine these two steps, this is what has happened over here. So you are remembering the topmost element in a variable y, and then you are removing it so that your stack from this much becomes this much. And then, so your first step is done. And what is the second step? The second step is to make the next recursive call. So you can call push bottom for x and the remaining stack. And then there is this final step, step number 3. So what is step number 3? It is to simply push whatever you had popped. So you had popped y, so you can push it by doing stack.push of y. Does the code make sense to everyone? Yes or no? Okay, cool. Okay, let's come to the next question. The next question is that we have been given a stack. Let's say 1, 2, 3, and 4. And we want to reverse this stack. Reversing means that currently if you read from bottom to top, it is 1, 2, 3, 4. I want to reverse it so that next time when I read from bottom to top, it should be 4, 3, 2, 1. Can you do that? How? Okay, let's talk about it. I'll first tell you that there is a very basic mistake that people make. I want all of you to hear to this basic mistake so that you don't make it again and again. They say that, okay, this is my current stack. Let's call it S1. So what I'll do is I'll take another stack S2. And we have already seen that when we empty this and push its contents into S2, it will appear reverted. Okay. So for instance, if I remove this 4 from here and push it here, and same thing if I do for 3, 2, 1, this is what I'll get. And that's it. Reversal has been done. So how many of you were thinking right now exactly like this? You can say yes if you were. Okay, cool. So it's very natural to think like this, and don't need to worry if you have thought like that. But let me tell you, here you have not reverted S1. Here you have imposed the revert picture of this in S2, but that is not I want. I want to revert S1 itself. So how to revert S1 itself? Now you will say that, hey, again, remove all the elements from here and push into that. But if you do that, it will become how it was. Okay, so what to do now? Yeah, one of you is saying use one more stack. That is right. Think, guys. Here you had 1, 2, 3, 4. Okay, here you had 1, 2, 3, 4. Now think of it in this manner. If there is a stack which contains the exact copy of this thing, which is it contains 1, 2, 3, 4 only. And at that point of time, if this is empty, then all that I need to do is I need to first push 4, then 3, then 2, then 1, which is I need to empty this and put its contents in this. So if I am able to create a stack which looks exactly how S1 was looking, then my job will be done. Is that making sense? Yes or no? Others, is that too tricky to understand or too trivial to understand? Yes, no, so that we move ahead. Yeah. Okay. Anyways, So yeah, I told you that whenever you empty a stack into another, you get the reverse picture of it. Again, if you empty this into another stack, S3, you will get a reverse picture of that. So let's say you had 1, 2, 3, 4. So if you pour all the elements from here to here, this is what you will get. Again, if you pour all the elements from here to here, then this is what you will get. So if you reverse something 2 times, that thing becomes exactly the same. And now what you can do is that now at this stage, you can say that the job of S1 and S2 is done. So now you can pour all the contents of S3 back into S1. So it's like you have used 2 auxiliary stacks, S2 and S3. So first you have emptied this into S2 and then you have emptied that into S3. Why? Because if you want to create the same copy of it, you have to reverse it 2 times. That is the reason you have used 2 stacks. And then finally, you have poured all the contents of this into that. If you do that, you will see 4 will come at the bottom and 1 will come at the top. Is it making sense to everyone? Yes or no? Okay, how many of you can implement this thing? Super easy to implement, right? Okay, one of you is saying instead of using 2 additional stack to create replica, can't we copy stack in another? How? Think of it. How exactly? See, you want to reverse it. And now you are saying that you have, emptied it into the other 4, 2, 3, 1. Now what should I do? You tell me that. Tell me the objective step. What to do? You want to again bring it here. So again, it will become 1, 2, 3, 4 from bottom to top. What purpose does it serve? It looks like if it was 1, 2, 3, 4 here, it should be 1, 2, 3, 4 somewhere else as well, so that you can pour it. Let's think about it. Not if we change the reference. Okay, so let's say you have S1, you have S2. You want this S1 to start pointing to this. You know, this is just a hack that you are doing in reality. Why this is just a hack? Because when somebody tells you to revert something, by default, he means do it in place. In place means within the same memory location. So if you brought it to some other memory location, changed your this, then how is this approach better than saying that, hey, S2 is reverted form of S1? This will again not be accepted. Yeah. Is that making sense to everyone, that how just by changing the reference is not going to? Okay, using OOB functionality, like what is OOB? Okay, whenever you talk about some standard operations, they have to be push, pop, and top, and is full, is empty only. Other operations are not standard operations. Anyways, so can somebody comment on the time complexity of this thing? Time complexity of reversing a stack if it initially has n elements. Yes, so I can say in order n time, I can transfer all the elements from here to here. Then in order n time, again, all the elements from here to here. And then in order n time, all the elements from there to there. So you might say it is n plus n plus n, which is 3n, but 3n, it can be approximated to order of n only. Okay, cool. So I have given you 2 good examples of where you can introduce a new operation on a stack by using the standard operations only. You are not allowed to use non-standard operations. Okay, cool. How many of you can try solving this question using recursion? Yes, no? Can you do that? It is a super interesting question when asked to solve using recursion, and that is your homework. When you go back today, please watch it on your dashboard, how it is done using recursion. Okay. It is not correct to say that using recursion, we will use only one auxiliary stack, because it depends upon how your recursion is crafted, because at times your recursion tree can be such that there are 2 parallel ongoing stacks. Okay, it all depends. So you have to check for that. Okay, now let's come to, 90% of the questions which you will be asked in stack will be based on a concept, and we are going to learn that concept now. That concept is of next greater element, super important. 90% of the questions will be based on this next greater element. Any questions till now? Feel free to ask. How Tower of Hanoi question is solved could have very high complexity. I mean, how do you want to solve Tower of Hanoi question for me? I can solve it in different ways. Which exact approach you are talking about? Think more about it, okay? It's not necessary that, like if you're using a stack, it might happen that the overall complexity is very, very high because it also depends upon your algorithm, right? So it's not correct to say that any question where you use stack will be solved in order 1 time or order n time, because it totally depends upon your algorithm. So now how are you planning to solve Tower of Hanoi, and how are you planning to solve it using a stack? How exactly? Think more about it. There are more ways to solve it. Okay, I can just use a plain recursion, or I can use a recurrence. And what is it exactly that you are trying to solve in Tower of Hanoi? Are you trying to figure out the number of ways, or are you trying to generate the number of ways? If you are trying to find out the number of ways, I can solve it using a mathematical recurrence. Okay, so answer these questions for yourself. If somebody asks you for number of ways, and number of ways itself is 1 billion, then you can't solve that question in lesser than order of 1 billion time, because you have to one by one create all those ways, right? But if it's just about tell me the count of ways, then it's just a mathematical problem. I can use a formula and get my job done, right? Okay, let's come to this question of next greater element. So let's say we have an integer array containing 4, 5, 2, 7, 3, 9. Okay, what according to you should be the meaning of next greater element? Or if you have ever heard of it? Okay, let's understand it first. This is made up of 3 different words: next, greater, element. Next means towards right side. Okay, greater means greater. It cannot be even equal. It has to be strictly greater. So let's consider this 4. When you consider this 4, next means towards its right side. So towards its right side, there are many elements which are greater than 4. So greater than 4, you have 5, you have 7, you have 9. But the next greater of 4 will be 5 only. The next greater of 4 will be 5 only. Why? Because that is the closest one towards its right, which is greater. See, even if it would have been 15 here, the next greater of 4 would have been 15, because that is the closest elements towards the right side, which is greater than 4. This is the definition of next greater. Does it make sense to everyone? What is next greater element? Yes or no? Can you tell me the next greater element for 5? For 5, it will be 7. Okay, cool. So let's write them quickly. For 4, it is 5. For 5, what is the next greater element? You said 7. For 2? So for 2, all these elements towards the right side should be considered, but only 7 and 9 are greater, and 7 is the closest one. Okay. For 7, the next greater is 9. For 3, the next greater is 9. For 9, there is no next greater, so you can say null, you can say -1. It depends upon what your question says for such elements. Yeah. Okay. How many of you can write a program to print the next greater element for every element in an array? Okay, can you tell me the idea? What will be the basic idea to write such a program? Nested for loop. Anyone else who is thinking about a nested for loop to get your job done? Yeah, exactly. That is the most intuitive approach that should come to every mind. Okay, cool. So when you look at this problem, I can say that, hey, let's say there is an element in an array. Let's say this element, this is X. So towards its right side, there might be many elements, but you are interested in the first element, which is greater than X. So let's say your X was 10 and you had 1, you had 0, you had 5, you had 9, you had 12, you had 6, you had 18. So for this 10, you would want to travel from here till the end, as long as you have not gotten an element which is strictly greater than 10. So if this is at index I, you want to move your j from I plus 1 to n minus 1. And the moment your a of j will be greater than a of I, you will break. It is important to break, right? Because consider this 10, this condition will click only for this 12. When you are traveling from here, this condition will first click for this 12 only, nothing before it. But the moment it has clicked, you must break, because if you do not break, this condition will click for 18 also, and you might end up saying that, hey, for 10, the next greater is 18. So all that you have to do is, for every element, travel all the way towards its right side. The moment you see you have found a greater element, that element will be its next greater. So break and then move on. Is it making sense to everyone? Yes or no? Okay, can you talk about the time complexity of this approach? Order n square, right? Yeah. Why will it be order n square? Because if you are doing it, let's say this was your array. When you are doing it for this element, you will have to travel all the way towards the right. What if the greater element than this is present at the last, or it is not present only, who knows? So you might have to travel all the way from beginning till the end. This is, you might have to travel for n minus 1 iterations. And then when you come here, you again will have to travel all the way towards its right side for n minus 2 elements. And then when you come here, you again have to travel for n minus 3 elements till 1, because when you are here, you just have to travel for one element. And the sum from 1 to n minus 1, it will roughly be order n square. Make sense to everyone that how the time complexity is order n square? Now, can we optimize it? Okay, so now is the most important concept that we are going to learn. Everyone, let's just look at it. So let's say we have got an array which contains 5, 4, 3, 2, 1. For now, just these many elements. Okay, what is the next greater of every element in this array? Next greater of 5, next greater of 4, 3, 2, 1. What is it? All null or all minus 1, because for no element, there is a greater element in the right side. Okay, cool. Can I say that this phenomena where every element has its next greater as null will happen if my array is sorted in, let me call it non-increasing order? Can I say it? It will always happen when the array is sorted in non-increasing order. Very, very easy to detect, right? Now, just think and tell me one thing. Let's say there was one more element in this array, and that was 4.5. If that was 4.5, then what would have happened? This 4.5 would have been next greater for 1, for 2, for 3, as well as for 4, but not for 5. If you carefully look, this would have been next greater for all these elements. Just think of it. Yes or no? Right? Now just take a look. So what really is happening is that this is an end. I had one over here. Let me write that one. This is an end. This is an end till which the array is sorted in non-increasing manner. Now, the moment you got an element, this element started removing from this end. started removing elements from this end. When I say started removing elements from this end, I mean to say it said that, hey, I am your next waiter, now you get out. Now it said, hey, now I am also your next waiter, you get out. It said, hey, now I am also your next waiter, you get out. I am your next waiter, you get out. Now I am not your next waiter, so let me just stay. So what is happening is there is one end, and that end is constantly being shrunk. Is it a stack-like behavior where a top is being shrunk or the top element is being popped? Yes or no? Do you see that? So what we can do is, imagine instead of storing these elements in an array, we were storing them up in a stack. And in this stack, you had 5, 4, 3, 2, and 1. Now comes this element 4.5. So keep it in your mind, this stack is sorted in non-increasing order. Okay. When you meet this 4.5 and you realize that, hey, this 4.5 is greater than the top of the stack, then you will feel great. Why you will feel great? Because this 4.5 definitely will be next greater element for this one, right? But it may be next greater element for many other items lying below 1 also. Like in this case, this 4.5 will be next greater for this 2 also. It will be next greater for this 3 also, and it will be next greater for this 4 also. So see what has happened in just very few number of operations, or in just four pop operations, you have been able to come up with what is the next greater of this, that, and that. And why it happened? Because you were using a stack. So the moment you kicked out an element, you had access to the next, had access to the next, and you had access to the next. And somehow the elements in the stack were always sorted. I'll come to this, how to ensure that. But do you get the point over here? How is this idea going to work? Yes or no? Okay, cool. Now you guys answer me one thing. Let's say the stack initially was like 5, 4, 3, 2, 1. So it was in non-increasing order. Correct? Now, you kicked the elements out as long as you kept getting elements which are smaller than 4.5. But the moment you saw that the current element of the stack happens to be greater than 4.5, then you will not pop it. Then you will simply push it into the stack. And why you will push it into the stack? The answer is very simple. Because who knows, after 4.5 there was some other element also, and now when you operate on this element, then that element might be assigned as next greater of this 4.5. So what really is happening is where you pop as long as you can pop, and then you push this element. So again, your resulting stack will be sorted in non-increasing order. Correct? It will always be ensured like that. So let's say the next element that you got after this is 3.5. Now when you see 3.5, you realize that, hey, this 3.5 is smaller than the top element, smaller than or equals to the top element. It means that this cannot be the next greater of anything in this stack, because this is smaller than 4.5. This means it will be smaller than everything else also. So in that case, you will simply push it. Now again, you can see that the stack is sorted from bottom till the top. And now let's say you met an element that was 4.75. When you meet 4.75, again, you will see that, hey, this 4.75 is greater than 3.5. So for 3.5, its next greater is 4.75. And let me remove it. And this 4.75 again is greater than 4.5, right? But now no longer, because now this 4.75 is smaller than this 5. So I'll simply push it. So at any instant of time, you will see that your stack is always sorted from bottom to top, because your algorithm is like that. You only pop as long as you can pop. And if you can't pop, you simply push. Is it making sense, the idea over here? Yes or no? Others, would you like to give some response to it so that we can move ahead? Okay. Cool. So now what I'll do is I'll take an input. So I generally don't consider dry run as the best way to learn things. The best way to learn things is to understand the concept and dry run in your own mind. But as some of you might be beginners, it's okay to have few dry runs. So let's take a look. When we solve this problem using iterations, we are exactly doing iterations. We are not using recursion, okay? So let's say we have 10, 7, 4, 2, 9, 10, 11, 3, 2. Now, you take a stack and keep it in your mind. Your stack always should be sorted for this approach to work. Because in this approach, what do? You stop popping the moment you see a greater element. And this idea is valid only if your stack is sorted. Because if your stack was not sorted, if let's say below 9 you had 11, and let's say you got something like 10. If you got something like 10, you might say that, hey, sorry, below 11 you had 9. Let's say below 11 you had 9. And now you got 10. Now looking at this 10, you say that, hey, this 10 is smaller than 11. Because it is smaller than 11, it will not be next greater for anything that is in the stack, but that is not true. So at any instant of time, your stack has to be sorted when seen from bottom to top. So how to initialize this stack? We can always initialize this stack with the first element, which is 10, because a stack containing one element is always sorted from bottom to top. There is no other element in it. Does that make sense? Why we can always initialize stack with the first element? Yes or no? Okay. So this is your first step of your algorithm, that initialize your stack with array of 0. Now run your algorithm from I equals to 1 till last. Okay. Currently you are looking at this element. What will be the first step? You compare this element with the top of the stack. If this element would have been greater than the top of the stack, let's say if it was 17, what would you have done? Tell me. You would have said that 17 is the next greater of 10 and you would have popped 10. Yes or no? But in this case, the element is 7, which is smaller than or equals to 10. So what will you do? You will simply push it. Some of you said if it was 17, then also you would have pushed it. Very bad. Why? If this 17 was greater than the top, you would have said that it is next greater element of 10, and you would have then pushed that 17. If you meant that, push it. So okay. Anyways, so you push this 7 now. Now you move on to the next element, which is this. Again, you compare that with the topmost element. So 4 is smaller than the top, so you will push it. Then you move on to the next element, 2, which again is smaller than the topmost, so you will push. So what is happening if your array I is smaller than the stack top, then you're simply pushing the element on the stack. Is that making sense to everyone? Yes or no? Right? Okay. So did you see in this process you have created a monotonic stack from bottom to top? Okay, now you move on to the next element, which is 9. What will you do now? Tell me. You compare this 9 with the top and you realize it is greater than the top. So what to do? Then your eyes should glow, because you should feel that, hey, now I have got that thing which is next greater for 2, but it might be next greater for many other elements also. So you'll say that, hey, this 9 is next greater for 2. Remove this 2. This 9 is next greater for 4 also. Remove this 4. This 9 is next greater for 7 also. Remove this 7. Now what to do? Is your 9 next greater for 10 also? The answer is no. So at this point of time, you will simply push it and move on to the next element. Is it making sense to everyone what's happening? Yes, no? Right? Okay, what to do now? You are at 10 and this 10 is greater than the topmost element. So again, you will be happy. You'll say for 9, the next greater is 10 and you will pop it. And what to do now? Is this 10 greater than this 10? No. So you will simply push it. And now you move on. So see what happened whenever you got an element which was greater than the top of the stack, you kept popping for a certain number of times. You stopped popping only if you got an element in the stack or you got the top element which was not strictly smaller. Okay, cool. You get this 11 again. What will you do? Compare it with the top. You will see that, hey, 11 is greater than 10. So that's the next greater element. And you pop again. Again, you compare it with the top. You'll say, hey, okay, what to do now? See, when you saw 11, you started popping. At some point of time, your stack might become empty like how it has become now. Because what if your current element is, let's say, 1 lakh, and it is so huge that it emptied all the stack? In that case, before you pop again from the stack, you have to check whether your stack is empty or not. So do you remember what I had told you at the beginning of the class? Whenever you are popping something from the stack or reading something from the stack, before doing that, you should check whether the stack is empty or not. Is it making sense to everyone? Yes or no? So this is a super important thing which we must not miss. At this point of time, the stack is empty. So I'll simply push this 11. Now again, the state of the stack, it is sorted. So now you come to 3. What will you do to this 3? It is smaller than the topmost element. So you'll just push it. Then you come to 2. This also is smaller than the topmost element. You will push it. Okay, so now you have iterated over everything, but still your stack is not empty. If the stack still contains some elements inside it, what does it physically mean according to you? How many of you agree with Surya? He's saying that those elements do not have any next greater, and that is totally correct. 11 has no next greater, 3 has no next greater, 2 has no next greater. So after your I has gone all the way till n, then you can just empty all the elements from this stack and you can say that, hey, they do not have any next greater. So you will remove this 2, null, remove this 3, null, remove this 11, null. So this is the algorithm that we'll be having. Does it make sense to everyone? How many of you feel you can code it? Let's do one thing. At least try to write the pseudocode. I want everyone to do that. Okay. I'm giving you some minutes. Try writing the pseudocode. See if you're able to do that or not. Meanwhile, if anyone would like to share his or her pseudocode, feel free to do that in the chat. I might check whether it is making sense or not. Okay, so I'm going to write pseudocode or code whatsoever will be able to. So let's look at the board, how to think of it. You guys tell me what should be our first step. Our input is an array. So looks like our first step should be to create a stack of integers, right? So we have a stack of integers. Give it some name. Now, before we move ahead, I'll ask you a very simple question. My question to you is, just tell me one thing. You want to have a next greater element array also. So you want to have NGEN. Why do you have this array? Because this is like your output array, because you want to store this thing, right? That for 10, the next greater is 11. For 7, the next greater is 9. You store all this data in an array. So I'm calling that array as NGE. So I have created these two things for me for now. Is it making sense to everyone? Why do we need NGE array and the other stack? Yeah? Okay, cool. Now, the key thing that I want you guys to answer for me is, let's say you have this 2. Okay, what is the next greater element for this 2? The next greater element for this 2 is 9, correct? Okay, makes sense. You have this 9. The next greater element for this 9 is 10. So in your NG array, at this slot, you would want to see 10, which is at index 0, 1, 2, 3, 4. At index 4, you would want to have 10. Now, if you're using a stack, do you remember what had happened? In your stack, you had pushed 10, then 7, then 4, then 2. And when you saw this 9 removed this, that, and then this 9 came here. Now, when you got this 10, with yourself, you see 9 over here. Will you be able to put this 10, which is the next greater of 9, at this slot in the NG array? Will you be able to do that just by seeing that you have 9 at the top of the stack? You see the question that I'm asking you. This 9 is at certain index I, and at the same index in NG of I, you want to put 10, which is the next greater of 9. Now my question is, if you're just using a stack, I was doing this thing for you in a very simple manner. I was telling you that, hey, for 9, the next greater is 10. And even the elements are repeated, like this 10 is different, this 10 is different. So you want to store in your NG array that NG of 0, which is next greater of 10, is 11. And you want to store over here something else, because for this 10, the answer might have been 12. So that is the very reason you have an NG array. But the point is that how do you place the correct NGE at the correct slot? How do you do that? You might not be able to do that if you just push integers in your stack. If you just push these elements 10, 7, 4 to 9, looking at this 9 in the stack, you will not be able to figure out what its index was. Do you get my point, what I'm trying to say? Yes or no? Right? So what to do? Certain people, what they do is they say, okay, along with element, we will push the index also. But that is not a wise thing to do. Why not just push index? Because if you just push the indices, let's say this index is I, this index is J, then from J you can say array J is the element. From I you can say array I is the element. So what I'll do is I'll maintain a stack, but it will not be a stack of integers, rather it will be a stack of indices of those integers. Is it making sense to everyone? Yes or no? Correct? So very, very important thing to understand. Cool. So let's come to our step 1. The step 1 was to initialize our stack with the first element. So what to do? What to do? I did not get, yeah. Okay, so what exactly did you not get? Did you get the problem that we are trying to solve, or did you not get the solution? The problem itself or the solution? Problem, okay. The problem is Do you know why we have created this ng array? Do you understand this thing? Yes, no? Yes, okay. So let's say ng of 9 is 10. You want to store that 10, if this index is 4, at NGE 4, you want to store 10. This is what you want to do, right? Yes or no? I think yes, right? Okay. Will you be able to do this thing just by using a stack? You have a stack and you had 10, 7, 4, 2, and then 9 came, and then you push that 9 here. Will you now be able to say that ng of 4 is 10 just by looking at this 9? Yes or no? How? Tell me how. Stack just contains 9. How do you figure out what was the index of 9? Do you still feel you will be able to figure out the index of 9? Yes, no. You can say yes if you still feel you will be able to figure out. No, so the problem is solved, right? You'll not be able to figure out. So instead of pushing the elements, you'll be pushing the indices of the elements. Is it now making sense to everyone else as well? A simple thing, but still very important for all to understand. Okay, cool. So what will be our initialization step? We want to initialize our stack with the first element. So should I push the element or should I push the index of element? I should push the index of the element, which is 0. So I should do stack dot push 0. Okay. Now, what was the next part of the algorithm? That you move from I equals to 1 to n minus 1. So for I equals to 1 to n minus 1, I need to do some task. Now comes the real fun. So what do? You are currently at some ith element. Let's say it is 9, and let's say at some point of time your stack is like that. What do you keep doing? As long as the current element, which is ith element, is greater than the top of the stack, you keep popping. So do you feel need of another loop inside this for loop, which will repeatedly pop the element? Yes or no? Right? Okay. So let that be a while loop for now. And here you would love to say that, hey, as long as my current element, what is my current element? It is at index I, so it is array I. So as long as my array I is greater than the top of the stack. Now, how do I get to know top of the stack? Top of the stack is s dot top. Now, say one thing. What is this s dot top? Is this s dot top the element or is this index of the element? This is index of the element. So what will you compare current element with? You will compare current element not with s dot top, but with a of s dot top. You understand my point? Yes or no? Correct? Okay. So as long as you see this condition is true, what will you do? You will say that, okay, whatever is the top of the stack, for that next greater element is a of I. And after doing that, you will kick that element. So you will do s dot pop. Is this piece of code making sense? How many figured that? Yeah, but is there something which is missing in this code? I am calling s dot top without even checking whether my stack is empty or not. If this element was 91, it would have popped 2, 4, 7, 10, and now the stack would have been empty, and it would again have checked for a of s dot top, and this would have given you runtime error. So before performing this check, you should first check whether your stack is empty or not. So I need to write one more condition. So while not of stack dot empty and this, so this and this, both the conditions should be true. So as long as both these conditions are true, I am free to do this thing on and on. Is it making sense that why is the need of that condition there? Yes or no? Okay, cool. So now I can say by the time this while loop is over, for array I, whatever elements could have been popped, they have already been popped. And then what to do? Then you just silently push array I into the stack. So you just do s dot push of the current element. What will you push? Will you push array I or will you push I? You will push I because it's your stack of indices only. That's it. This is the code for you. Okay, is it all done? By the time this for loop would be over, would I know about next greater element of everything? The answer is no, because at the end, it might so happen that elements that do not have any next greater are still lined up in the stack. So as a final step, what you can do is you can empty the stack while not of stack.empty. You just read the top element and you say that ng of that is null, and then you pop. So this final while loop can be written by you on your own. Does everyone understand what's the need of that final while loop? Yes, no? Yeah. Okay. So this algorithm, can you please repeat first while loop? First while loop. Okay. So let me ask you this. Let's say this stack contains 10, 7, 4, 2. When you get this 9, using this 9, you remove 2, 4, 7. You understand that? So this code is exactly doing that. And now you should try to understand how. Okay. So it's very simple. You indeed are pushing the indices of the elements. So you have pushed 0. The index of 7 is 1. It is 2. It is 3. So for current element, for a of I, if it is greater than a of s dot top, if it is greater than a of 3, then you come inside and you pop and do something. Very easy to understand. I mean, I shouldn't be explaining it again. You should be able to figure that out. If not, you can ask that. Yeah. Okay, cool. What is the time complexity of all this algorithm? The time complexity of the brute force approach was order n squared. So is it any better, worse, or same? You know, the common notion of people is that what they do is when they say that there are two loops, they say, hey, it must be order n square. No, it's not like that. Nobody defined that rule. Okay. When you look at this problem, answer me one thing. Any element that you are considering, you are pushing it once and you are popping it once from the stack. And the real logic that you have inside over here is of push pop only. So any element is being pushed once and popped once. Can I say that? Yes or no? Right? So if there are n elements, all those n elements will be pushed once and popped once at some stage. So there are two operations happening for each element, and because there are n elements, total number of operations will be 2 into n. Hence, the time complexity is nothing but order of n. Is that making sense to everyone? How the time complexity here is order n? Yeah. Is there some extra space also? The answer is yes, because we are using an extra stack. Cool. So that will be it for today. So I have told you all the essential things about stack. Tomorrow when we meet, we'll initiate queues, and then we'll also go on till linked lists. But it's your responsibility that when you go back today, please watch your dashboard of stack. You will see it is flooded with very interesting problems on the same concept. Those of you who understood and enjoyed this concept, you will love the problems. And then you will become expert of stacks. I mean, almost every question that you will see in stack, you will realize that, hey, it is a concept based on this idea itself. But you can find plenty on your dashboard, plenty other concepts as well. So please start spending time if you're not doing that already. It'll be super helpful. Cool. So that's it. Let's meet again tomorrow, and that will be it. Bye and have a good day.